For over a century, we believe Titanic tore apart in minutes from a massive hull gash. But the most advanced 3D scan ever made at 3,800 meters just proved we were wrong. Built from 700,000 high-resolution images and 16 terabytes of data, this digital twin reveals not a single catastrophic break, but 6 razor-thin slits along 300 feet, and a drawn-out, violent breakup that defies every textbook. The model even uncovers evidence of heroic actions in the engine room that kept hundreds alive, and pinpoints artifacts exactly as testimonies described. If Titanic's final moments are nothing like we thought, what other truths has the ocean been hiding all this time? 3 weeks at sea. That's what it took for the expedition team to capture every angle of Titanic's remains. 2 remotely operated vehicles, Romeo and Juliet, worked in tandem, launching from the deck before dawn and vanishing into the blackness below. At 3,800 meters, the pressure is nearly 400 times what we feel at the surface. Every dive was a test, not just of technology, but of nerve. Pilots steered past jagged steel, collapsed decks, and a maze of twisted beams, relying on sonar and laser grids to keep the ROVs clear of entanglement. Flashlights barely cut through the silt and darkness. Navigation meant constant adjustments. Currents could shift in minutes, and a wrong move risked losing a $1 million vehicle to a tangle of cables or a sudden collapse. Each grid sweep demanded precision. The team mapped the site in overlapping passes. Every image needed at least 60% overlap with the next, so nothing was missed. That meant Romeo and Juliet crisscrossed the debris field dozens of times, sometimes pausing for hours to let stirred-up sediment settle before taking the next shot. The cameras they carried weren't ordinary. They were custom-built for low light, paired with powerful flashes and calibrated lasers. Every photo was tagged with its exact position and time, building a digital jigsaw puzzle out of more than 700,000 images. Engineers and deck crew worked around the clock, maintaining the ROVs after each dive. Saltwater corroded connectors, deep-sea pressure warped housings, and the cold threatened batteries and electronics. Yet, the system held. By the end of the mission, the team had gathered 16 terabytes of raw data. Every rivet, every crumpled panel, every artifact mapped in millimeter detail. What once took years of guesswork could now be reconstructed with forensic accuracy, setting the stage for a new kind of investigation. Once the last ROV returned to the surface, the real work began for the photogrammetry team. Inside the mission control lab, specialists faced a mountain of raw data, over 700,000 images, each tagged with precise coordinates and timestamps. The first step was to sift through this archive, sorting out frames blurred by drifting silt or interrupted by stray cables. Only the clearest, most evenly lit shots made the cut. Algorithms then searched for overlapping features, matching rivet lines, portholes, and torn steel across thousands of photos to stitch them together in 3 dimensions. To guarantee accuracy, the team relied on a series of calibration bars placed on the wreck and natural reference points, like the serial numbers stamped on the propeller and the measured width of boiler valves. These anchors allowed the software to scale the model with remarkable precision, down to just 1 or 2 millimeters of error in the best lit areas. In zones where geometry was complex or shadows deepened, manual checks and redundant passes helped catch distortions. Outlier images were flagged automatically, and entire sections could be reprocessed if residuals crept above strict quality thresholds. Laser scans supplemented the optical data, projecting a grid of known distance onto the ship's surface. This cross-verification caught any drift or subtle warping in the photogrammetry mesh. Every segment of the wreck, bow to stern, debris field to engine room, was subjected to quality assurance gates. Only after passing these checks did the model advance to the next stage. The result? A digital twin whose measurements could be trusted not just for visual storytelling, but for forensic analysis, engineering review, and historical record. With the model certified, the team could now examine Titanic's final moments in a way that was never possible before. One rivet, one artifact, one scar at a time. The digital twin brings the Titanic's final resting place into sharp relief, a vast uneven canvas of steel and silt nearly 4,000 meters below the waves. The bow sits upright, its prow still angled as if straining toward New York, embedded gently in the seabed at about 3,800 meters. 14 meters deeper, the stern lies collapsed and almost unrecognizable, a tangled mass of decks and machinery pancaked by its violent descent. Between these two hulks stretches a debris corridor nearly 600 meters long, scattered with thousands of artifacts, everything from engine parts to porcelain, shoes, and deck chairs, each frozen in place by the pressure and cold. Navigation analysts mapped out the site with the precision of a surveyor. The bow and stern rest on a subtle incline, their separation and depth difference now measured to within millimeters. The bow's higher perch reveals how it embedded gently, dissipating much of its energy into the soft seabed. In contrast, the stern's deeper resting place and twisted wreckage point to a catastrophic spinning fall, its structure torn apart by stress and water pressure before smashing into the ocean floor. The debris field itself tells a story of destruction and dispersal. Heavier machinery and structural beams cluster near the stern, while lighter objects, suitcases, dishes, fragments of wood, fan out across the corridor, carried by currents and the force of the breakup. Analysts trace the gradient of debris, revealing how energy from the sinking ship spread outward, scattering artifacts in patterns that match the flow of water and the ship's final moments. Some items landed almost gently, others were hurled and shattered, creating pockets of concentrated wreckage and long, thin trails of scattered metal and personal effects. This spatial map is more than a technical achievement. It provides the first complete, forensic view of how Titanic's breakup played out across the sea floor. Every bearing, every depth shift, every cluster of debris adds a new layer to the understanding of what happened that night, setting the stage for a deeper look at the human stories and mechanical failures preserved in the wreck. A child's shoe, size 8, rests at grid coordinate 42.175 by 17.603, its leather warped, the buckle still faintly visible. Nearby, a trunk split open, spilling its contents across the silt, a comb, a brush, a handful of coins. Each item is anchored to a precise moment, a specific deck, a lost name. The new digital twin connects these objects with the evacuation timeline. Bunks in third class are crushed flat, the metal frames folded in on themselves, mapping exactly to where the hull bent and water rushed in. Scorched electrical panels line the passage outside the Marconi room, copper wiring fused by heat and pressure. These are not just forensic clues, they are silent witnesses to the chaos and courage of the final hours. Analysts trace the path of a deck chair from the boat deck to the debris field, its curved wood, snapped but still recognizable, found at 43.892 by 18.021. A child's shoe, once dismissed as a stray artifact, now matches the timeline of a family last seen in Lifeboat 14's vicinity. Survivors spoke of lights burning even as the stern lifted skyward. The scan confirms this. Wiring arcs and burned insulation run through the upper decks, proof that engineers kept power flowing until the end. Oral historians, working alongside the mapping team, cross-reference these findings with family accounts passed down for generations. A battered trunk found near the stern matches a passenger manifest entry, its owner never identified, but the items inside suggest a young woman traveling alone. For descendants, these details bring a measure of closure. The digital model does not simply catalog loss, it honors memory. Each mapped artifact, each scarred panel, adds the mechanical story to real lives. The Titanic's final chapter is now written not just in steel and silt, but in the echoes of those who never returned. Titanic's reputation for safety gets rested on a simple promise. Watertight bulkheads could contain disaster. Yet the digital twin reveals a different reality. The ship's hull was divided into 16 main compartments by steel walls, or bulkheads, each designed to stop water from flooding the entire vessel. But these barriers did not reach up to the main deck. Instead, most stopped 2 decks short, leaving a gap overhead. On paper, Titanic could stay afloat with any 2 or even 4 compartments flooded. The iceberg changed that equation in seconds. The 3D model shows how 6 razor-thin slits, stretching across 300 feet of the starboard side, allowed water to pour into one compartment after another. As each filled, the water simply spilled over the top of the next bulkhead, like a rising tide flowing down a staircase. This step-over flooding was not a freak accident. It was a direct result of the design. Naval architects had argued that making the bulkheads higher would cost space and money. Some even warned that a collision breaching more than 4 compartments would be fatal. The new scan validates those warnings with forensic clarity. Cross-section views from the digital twin show the precise heights of each bulkhead mapped against the path of the flooding. Simulations built on these measurements track the water's progress minute by minute. Once the 5th and 6th compartments were breached, the ship's fate was sealed. The so-called unsinkable claim collapsed under the weight of its own engineering. Titanic's bulkheads slowed the disaster, but they could not stop it. The real story, now mapped in steel and silt, is one of cascading failure, a lesson written not in marketing, but in metal. Titanic's story has always been haunted by legends: steel so brittle it shattered, a rudder too small to save her, rescue ships close enough to turn tragedy into survival. The digital twin cuts through the fog with forensic clarity. Hydrodynamic models built from the scan confirm what naval architects long suspected. Titanic's rudder, just 1.5% of her hull's cross-section, was underpowered for a ship of her length and speed. In the final 37 seconds after the iceberg was spotted, the helm swung hard, but the ship's inertia and the rudder's modest size meant only a few degrees of course change, far too little, too late. The old claim that she could only turn 0.7 degrees in that window isn't supported by any simulation or maneuvering log. What's clear is that the response was sluggish. The design a compromise between tradition and ambition. Material myths fall under similar scrutiny. Metallurgical assays of hull plates and rivets, cross-referenced with the 3D scan, reveal steel and iron consistent with early 20th century standards. Some rivets show cold brittleness, but the pattern of failure, 6 razor-thin slits over 300 feet, matches dynamic stress and hull geometry, not a single catastrophic flaw. The scan overlays these findings with mapped stress paths, showing how flooding and torsion, not just material limitations, doomed the ship. Wireless logs and artifact mapping address the rescue question. The Californian, often cast as the mist savior, was separated by ice fields and darkness. The digital model reconstructs sightlines and distances. No clear path, no easy rescue. The Marconi room's scorched panels and fused wiring confirm that Titanic's crew kept signals and lights running as long as possible. Survivor accounts of lights burning to the end are now backed by physical evidence. Rerouted cables, burned insulation, and open steam valves locked in place. Myths yield to measured data, and the digital twin becomes the final arbiter, clearing away a century's worth of narrative clutter. With the digital twin now complete, attention turns to what the data can actually do. Naval architects and forensic engineers are preparing to run the most detailed simulations ever attempted on Titanic's structure. Using the millimeter-accurate scan as a baseline, they will test how water moved through the ship, minute by minute, compartment by compartment, using advanced hydrodynamic modeling. One scenario under discussion asks a classic question. If the collision bulkhead had been extended by just 10 feet, would it have held back the flooding long enough to keep Titanic afloat? While no formal experiment is scheduled yet, the groundwork is laid. Every bulkhead, deck beam, and rivet is now mapped, allowing researchers to build virtual disaster models and stress test alternate designs. Alongside these digital trials, a new search is being planned for missing midship sections, using chirp sonar and sub-bottom profiling to probe beneath the sediment. The digital twin serves as the master map, guiding ROVs and sonar teams to precise coordinates where buried fragments might still lie. For the first time, theory and fieldwork can operate in sync, pushing Titanic research into a new era of evidence-driven inquiry. For the first time, the full Titanic digital twin is available to the public, down to every visible rivet, deck beam, and artifact. Researchers and educators can now access a 16-terabyte dataset, complete with time-stamped images, laser scans, and navigational logs. This open release transforms the site from a closed archive into a living resource. Anyone with the right tools can measure hull slits, match artifact positions, or cross-reference survivor accounts with physical evidence. Data dashboards allow users to trace the path of a single suitcase or examine the precise geometry of a torn steel plate. Historians are already using these tools to revisit the original British and American inquiry transcripts, mapping testimony against the actual wreck layout for the first time. Disputed claims about the sequence of the breakup, the location of lifeboats, or the persistence of lights can now be tested against forensic evidence. Networks of scholars, teachers, and citizen researchers are forming around the dataset, sharing annotations and new findings. This approach encourages ongoing inquiry, not just passive viewing. The Titanic story is no longer fixed in museum glass. It's open to re-examination, debate, and discovery by anyone willing to engage with the evidence. The scan revealed that the ship broke apart slowly along 6 razor-thin slits stretching 300 feet, not from a single gash. Forensic evidence now matches survivor accounts. The lights stayed on to the end, and the breakup was more violent and prolonged than once believed. The model pinpoints the engine crew's actions, showing buckled grates and locked valves that kept power flowing for precious extra minutes. Public release of the digital twin and artifact map means that, for the first time, anyone can examine the hard evidence. As new simulations and deep-sea searches continue, Titanic's legacy shifts from myth to measurable fact, grounded in the metal, the data, and the choices made on that night in 1912.